Howdy, howdy. This is Mr. Potter. What we're going to do in this next chapter is we're going to be talking a little bit more about limits because we need to take into consideration what happens when the values that we're reaching don't exist. We're going to be dealing with a lot of situations where functions don't exist or limits appear not to exist, and we need some stronger tools than we had back in chapter 2 to evaluate these limits. So we're starting over here with section 8.2, and we're going to be talking about a rule called L'Hopital's rule. So what we have been doing is we've been taking a look at situations of this form, this idea that I'll have the limit as x approaches some value of a of f of x over g of x. And one of the things we notice is that if I could not directly substitute, one of the culprits was the fact that f of a ended up being 0 and g of a ended up being 0. And so I ended up with this 0 over 0 situation, and that often meant that I had a common factor that I could divide out, or it often meant that I was dealing with some other issue, which we had to deal with graphically or using some algebra tricks. But what I want to do is I want to introduce this concept called L'Hopital's rule. So L'Hopital was a French mathematician, L apostrophe H O P I T A L, and sometimes you'll see this L with an accent on it. But L'Hopital's rule basically says that if I'm looking for the limit as x approaches some value of a of a ratio of two functions, and this is true that f of a is 0 and g of a is 0, then this actually ends up being equal to the limit as x approaches a of f prime of a over g prime of a. And so this is a very, very powerful tool, the idea that we know that derivatives often will simplify either by reducing the degree or getting rid of constant terms. And so sometimes the derivative functions that we're going to be dealing with are going to be much easier to work with. So I want to start off by doing a little bit of a proof of this. And so I want to start by talking about, what does f prime of a mean? And we know that f prime of a is a limit, and we've actually seen several ways that we could write this limit. But because I have this here, I want to use the symmetric form of the definition of the derivative. So I want to look for the limit as x approaches a of f of x minus f of a over x minus a. And this was one of the forms of the definition of the derivative that we had back in chapter 3. So if I want to look for the expression f prime of a over g prime of a, that should be this ratio divided by g of x minus g of a over x minus a. The limit of this whole complex fraction. And so what I want to do is I want to simplify this fraction. And I want to simplify in a couple of ways. First, I do notice that I end up with the limit as x approaches a. In the numerator, I've got a 1 over x minus a term times f of x minus f of a. And in the denominator, I have that same term, f x minus a times g of x minus g of a. And of course, one of the things that we've noted algebraically is when I have a common factor in the numerator and denominator, I can go ahead and divide those terms out. But the other thing I notice here is I've got the limit as x approaches a of f of x minus f of a. Well, f of x is my function, but we said that f of a was 0. And similarly, we said that g of a was also 0. So I'm left with the limit as x approaches a of f of x over g of x. Now this L'Hopital's rule that I have here is actually a little bit stronger. This idea that if I want to find this limit, I just need to find this limit. Of course, if f prime and g prime are already defined, then it's just a matter of simple substitution. And we'll do several examples showing that. So I actually want to start with some examples of limits that we've seen before. And so there's two ideas that I want to talk about. The first was this idea, let's say I've got the limit as x approaches 2 of x squared minus 4x plus 4 over x squared minus 4. So I've got an algebraic expression in the numerator and an algebraic expression in the denominator. And if I try and substitute, I'm going to see 0 divided by 0. And this actually has a special term for us. We call this an indeterminate form. And the reason we call it an indeterminate form is because at this point, I don't know if it's actually going to be an undefined expression or a defined expression. Maybe this limit will go to infinity. Maybe this limit will go to 0, maybe this limit will go to a constant. I don't know that at this point. But what we did in the past is we would simplify this algebraically. We would factor this out to x minus 2 times x minus 2. And the denominator is difference of squares, x minus 2, x plus 2. And we would cancel out our common factor in the numerator and denominator. But what I want to do is I want to take this L'Hopital's concept. In other words, I say that the limit of this function f of x over g of x, since f of a is equal to 0 and g of a is equal to 0, this should be equal to the limit as x approaches 2 of the ratio of the derivatives. So if I take the derivative of x squared minus 4x plus 4, I get 2x minus 4. And if I take the derivative of the denominator, I get 2x. And I had an issue substituting 2 into my original f of x and g of x. I don't have that issue anymore. It's rather straightforward to substitute 2 into both of these expressions, because 2 is in the domain of each of these expressions. And so I end up with 2 times 2 minus 4 over 2 times 2. And so I get 0 over 4, which is 0. Which means this function, as I'm approaching the value of x equals 2, at the point where x equals 2, I'm actually going to have a hole in my function at 0. The limit approaches from the left and from the right, whatever the behavior of my function is, but at that point I've got a limit. The limit exists, and the limit's value is equal to 0. I wanted to do one more example that we did. This is one that we've seen quite a bit, and one that tends to show up on multiple AP exams in lots of different forms. The limit as x approaches 0 of sine of x over x. And the way that we treated it originally back in chapter 2 is we looked at it from a graphical standpoint, and we noticed that the graph of this function tended to pass through the point 0, 1. We said that this limit had to be equal to 1. Again, if I try and substitute x equals 0, I get sine of 0, which is 0. And if x is 0, then I get 0. So I get the same indeterminate form. But I want to take a look at it from L'Hopital's rule. L'Hopital's rule says the ratio of two functions as x approaches a particular value is equal to the limit as x approaches that same value of the derivative of the top function, which would be cosine of x, over the derivative of the bottom function, which is 1. And this is a lot easier to substitute in because 0 is actually in the domain of both of these functions. Cosine of 0 is 1, and of course the constant function will always be 1. And so I get this limit to be 1. Notice that both of these limits that I got in this example and in the tan example, both of these limits are exactly the same as what we expected back in chapter 2. So we have these techniques, this algebraic application or this graphical application to try and solve limits. But now we've got another tool in our belt, this idea of L'Hopital's rule. If the limit doesn't exist, then we're going to look at the ratio of the derivatives and try and evaluate that limit. So I want to go through a couple more examples of this. So let's take a look at the limit as x approaches 1 of the cubed root of x minus 1 over x minus 1. And again, if I try and substitute x equals 1, I'm going to have the cubed root of 1 minus 1 over 1 minus 1. So I get that indeterminate form, 0 over 0. And I could try and factor this, but it's going to be rather difficult. What will actually happen is I'll have to treat this as a difference of cubes in order to factor out a term. It's going to be much more straightforward to actually go in and take the derivative of the numerator and the denominator. Remember that this is really x to the 1/3 power that I've got here. And so the derivative of that would be 1/3 x to the negative 2/3 minus 0 over 1 minus 0. So notice that the act of taking the derivative for my f of x and for my g of x makes this a simpler function. As a matter of fact, at this point, I can actually substitute x equals 1, because I'm going to have 1/3 times 1 to the negative 2/3 over 1. And this ends up just being 1/3. Which means this function, however it behaves, has to pass through a hole at the point 1, 1/3. So I'm going to do another example similar to this. So let's take a look at the limit as x approaches pi over 2 of 1 minus the sine of x over 1 plus the cosine of 2x. And I'm looking at this. When I substitute pi over 2 into this, I'm going to end up with sine of pi over 2, which is 1. So this gives me 1 minus the sine of pi over 2, which is 0. And in the denominator, cosine of pi is negative 1, so this becomes 1 plus negative 1, which is 0. So I end up with this indeterminate form again. And if I take the derivative, I'm actually going to end up with a simpler function as well. So the limit of f of x over g of x as x approaches pi over 2 should be equal to the limit as x approaches pi over 2 of the derivative. So I need to take the derivative of this numerator, which is negative cosine x, and I need to take the derivative of the denominator, which would be negative sine of 2x times 2, because of the chain rule. And now at this point, if I try and substitute cosine of pi over 2 is 0, sine of pi is 0, which is going to cause me some more problems. I still end up with this 0 over 0 business. And so I'm going to need to go through this one more time, because this is still some new f of x and some new g of x, and L'Hopital's rule says I should be able to do this again. So let's go ahead and try this once more with feeling. So I'm looking for the limit as x approaches pi over 2 of, if I take the derivative of this, I'm going to end up with a positive sine x. And if I take the derivative down here, this is going to be negative cosine of 2x times. Now I've got another 2 that pops out, so I end up with 4. And in looking at this, when I try and substitute now, substituting sine of pi over 2, sine of pi over 2 tends to 1, but cosine of pi this is going to be negative 1, which I'm multiplying by a negative, and then multiplying by 4. So I end up with 1/4. So the act of doing this over and over again gives me the possibility of evaluating the limit. I'm not limited to just using L'Hopital's one time, but in fact I can use L'Hopital's as many times as I need, as long as I end up with that indeterminate form. As long as I have the indeterminate form, I can use L'Hopital's rule. And so this allows me to do things repeatedly. There's one other example that I wanted to do here. I wanted to take a look at the limit as x approaches 0 of tangent of x over x squared. Now, I know that the tangent of 0 is 0, and I know that 0 squared is 0. So I get that indeterminate form, and so L'Hopital's rule will apply in this case. So when I try and take the derivative of the numerator, I get secant squared of x, and then taking the derivative of the denominator gives me 2x. And so of course, my first instinct is to try and substitute. If I substitute 0 into secant squared, well, that's 1 over cosine, and cosine of 0 is 1. So this becomes 1. But down here I end up with 2 times 0. And so I don't have an indeterminate form. Because it's not in indeterminate form, it's not 0 over 0. I don't see that here. I see a constant over 0, which means my denominator appears to be increasing without bound. So here this limit is undefined. And this is really a key point here. Even though I have this tool for L'Hopital's rule that allows me to evaluate some limits that have an indeterminate form, it's still possible for me to get an undefined limit. L'Hopital's rule doesn't guarantee that every function has a limit. As a matter of fact, if I look at the graph of this function, I'm going to see an asymptote here and an asymptote here. So I'm going to see a vertical asymptote where my function does not exist and no limit exists. Just because I have L'Hopital's rule as a tool does not mean that I magically gain the ability to get a limit for functions that didn't have one. So I want to do one last example of something like this, something where taking L'Hopital's rule once isn't enough because I still end up with an indeterminate form. So I want to do one last example here. I want to look at the limit as x approaches 0 of cosine of x minus 1 over e to the x minus x minus 1. So right now when I try and substitute x equals 0, I get cosine of 0, which is 1, and subtracting 1 gives me a 0 in the numerator. Down here I'm going to have e to the 0, which is 1, minus 0, minus 1. So I get 0 in the bottom. I get this indeterminate form, and so I have access to L'Hopital's rule. So I need to take the derivative of the numerator and the derivative of the denominator. Derivative of the numerator here would be negative sine x minus 0, which I'm not going to write, over e to the x minus the derivative of x minus the derivative of 0. The problem here is when I try and substitute, I'm going to have negative sine of 0, which is 0. And in the denominator, I'll have e to the 0 minus 1, which is 0. I get indeterminate form again. Of course, that means that I can use L'Hopital's rule again. And so this is going to evaluate to the limit as x approaches 0. When I take the derivative of negative sine x, I get negative cosine of x. And taking the derivative of e to the x minus 1 gives me just e to the x. And now I have the leisure of substituting and getting an actual answer. Because as x approaches 0, cosine goes to 1, and so I have negative 1 in my numerator, and substituting a 0 in the denominator gives me e to the 0, which is 1. So my limit evaluates to negative 1. So two key points here are using this idea of L'Hopital's rule. One is I really need this indeterminate form. This is what determines whether or not I can actually use L'Hopital's rule. If I don't have the indeterminate form, then I have to find the limit some other way, either by using the algebra techniques that we've talked about, or using the graphing techniques. And the other thing is that every time I use L'Hopital's rule, I'm taking the derivative of the numerator and dividing by the derivative of the denominator, and this is not the quotient rule. I am not taking the derivative of a ratio of two functions. I'm taking the derivative of the numerator and putting it over the derivative of the denominator. I am not using the quotient rule. And that's a mistake that a lot of novices will do on these problems. So go ahead and work on the assignment. And once again, this is Mr. Potter. Thank you for watching. Have a great day.